Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over gas stoichiometry involving gases. So let's get into this. Excuse me. So first, normal stoichiometry is where you are using a balanced equation and you're using molecules, you're using masses and molar masses to convert from one thing to another using that balanced equation to help you get the mole ratio and convert from one thing to the other. So we can use this stoichiometry if we have gases in our reactions as well. And so if our reactions involve gases, then that's going to bring in gas laws. So, because we still need mole ratios to convert from one substance to another, right? If I want to know how much reactant is needed to produce a certain amount of product, or if I want to know how much product is going to be formed from a certain amount of reactant, I need the mole ratio in order to help me convert from one thing to the other. And that mole ratio is going to come from the balanced equation. So that's why it's called stoichiometry. So in this case, we may need to use gas laws to find the number of moles of a substance that we're given, right? So if we're given, say, the amount of a certain gas, like say we're given temperature, pressure, and so on, and we need to find the moles from that to in order to use our mole ratio. So here we have the roadmap that you should be somewhat familiar with. So in our normal stoichiometry, we're looking at this top part here. So we're given the mass of some substance. It could be a product or it could be a reactant, and it's in grams. Or if it's not in grams, like maybe it's in kilograms or pounds or something like that, then you would need to convert it to grams. And then when you go from grams to moles of A using the molar mass. So you'd use the molar mass to convert moles of mass of A to moles of A. And then once you're here, you can use the mole ratio between A and B in your balanced equation. So this comes from the balanced equation. And this mole ratio helps us to convert from moles of A to moles of B. And then if you wanted to find the mass of B, then you would have to use the molar mass of B to find the mass of B. So this is basically your normal stoichiometry problem. Now, if our balanced equation or if our reaction involves gases in any way, then we may need to use the ideal gas law to help us to convert the information that we know about the gas to moles. And so here is the added part to our roadmap. So here I have pressure, volume, and temperature of substance A. I can use that information to find the moles of A using PV equals nRT. So, and then once I have moles of A, now I'm in the regular roadmap. I'm in the normal stoichiometry roadmap, and I can go anywhere here. So I could have a problem where it gives me liters of a certain amount of reactant gas. And so I want to know then how many liters of a product gas I may find. In order to do that problem, I would have to follow the roadmap. So I would have to first take the pressure, volume, and temperature they give me in the problem for that gas, for gas A. I would then plug that into PV equals nRT, find the number of moles. Once I got the moles of A, then I use the mole ratio from my balanced equation to find moles of B. And then I can use PV equals nRT again to find whatever it is I need. So if I'm trying to find the liters, then I would use the pressure, the temperature, and the moles of B that I have found to find the liters of my product gas. So this is the roadmap that you would use. So you can use PV equals nRT, or sometimes you can use molar volumes to help you convert from liters directly to moles. And so remember that STP, remember standard temperature and pressure. 1 mole of a gas is equal to 22.4 liters. That is under standard temperature and pressure. And again, just to remind you, standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. Now, you could also use SATP, which is the standard ambient temperature. So standard ambient temperature is 25 degrees Celsius, and then standard pressure. So under standard ambient temperature and pressure, 1 mole of a gas is equal to 24.8 liters. So you could use that as a conversion factor to convert between volume of your gas and moles. And so again, that's going to be 1 atmosphere that under the conditions of 1 atmosphere and 25 degrees Celsius. And so you could use those to convert to moles. And then once you got moles, you're now able to go back and forth on the roadmap. Okay, so I hope this was clear. At this point, I am going to now do 3 example problems to show you how this works. Okay, so here is example problem number 1. So example problem number 1, we have CH4. CH4 burns in oxygen and it produces carbon dioxide and water, gaseous carbon dioxide. And we have a 1.22 liter cylinder at 15 degrees Celsius, and that has a pressure of 328 kilopascals. And so the first part A is asking us what volume of O2 at 100 kilopascals and 298 Kelvin will be required to react completely with all of the CH4. So we're given information regarding the CH4 here, and we want to know, well, what volume of O2 will react completely with that. So the first thing we want to do is get a balanced equation. So the balanced equation is going to be CH4 gas plus O2 gas, and that's going to be a 2. And so that's going to produce CO2 gas plus water vapor or gaseous water, and there should be a 2 in front of there as well. And so here is our balanced equation. And so for stoichiometry, you always need a balanced equation so you can get that mole ratio. Now, the next thing we need to do is we need to follow our roadmap. In this case, since we're given pressures and volumes and temperatures of gases, we're going to need to use our ideal gas law to convert the volume of a gas into moles. So we need to get the moles. So first thing we're going to need to do is take our volume of a gas and we're going to convert that to moles using PV equals nRT. So volume of gas A to moles of gas A. And then from moles of gas A, we're going to have to go to moles of B. And then from moles of B, we're going to have to get volume of B, again, using the ideal gas law, PV equals nRT. And again, going from moles of A to moles of B, we're going to use our mole ratio in the balanced equation. So this is our roadmap. So first thing we want to do is take the information and find out how many moles we have. So if we use the information here, we can figure out how many moles of our CH4. So we want to go from moles of CH4, right? So that's the starting information that we've got. And they're asking us for a volume of oxygen. So oxygen is going to be our substance B. So we're going to go from A to B. And here the CH4, the methane is our A. So we're going to figure out, well, how many moles of methane do we have to start with? So we're going to have to take this information. We're going to convert temperature into Kelvin, right? So remember, temperature has to be in Kelvin. So 15 degrees plus, oops. Sorry about that. So 15 degrees plus 273 Kelvin. And that's going to give us 288 Kelvin. So there's our temperature. And we've got liters. And we got kilopascals. Now, you may be used to using the constant, the ideal gas law constant, R, in atmosphere liters per Kelvin mole, which would be 0.08206 atmosphere liters per Kelvin mole. In that case, you would have to convert this to atmospheres. But if you know, or you can look up, the ideal gas law constant R in terms of kilopascals and liters, then you could use this. So we're going to go ahead and use this. So it'll save us a step. So all you do now is take your ideal gas law. So the number of moles is equal to PV over RT, and if you plug in everything, so we got the pressure 328 kilopascals multiplied by the volume, which is 1.22 liters, divided by R, which is 8.31, and again that's going to be kilopascals liters over mole Kelvin multiplied by the temperature, which is 288 Kelvin. So 288 Kelvin. Okay, so then make sure everything cancels out. So kilopascals cancels out, liters cancels out, and Kelvin cancels out, leaving moles, which is what we want. So when we calculate that out, we get 0.167 moles of CH4. So we got our moles of CH4. So now we're here in our roadmap. So the next thing to do is use the mole ratio to convert moles of A to moles of B using the mole ratio. So we're interested in methane and oxygen, so it's a 1-to-2 ratio. So then we set up our conversion factor. So we take the 0.167 moles of CH4, and we use the mole ratio 2-to-1. So moles of CH4 are going to go on the bottom, so that's 1 mole. So 1 mole of CH4 on the bottom, 2 moles of O2 on top. So moles of CH4 cancel out, and we get, for our moles, 0.334. So I already have this calculated out. Oops. So that's going to be moles of oxygen. So now I have my moles of oxygen. So now I'm here on my roadmap. So now all I need to do is take the number of moles that I have and then use the information they gave me. So I have 100 kilopascals, 298 Kelvin, And so now I can take that and use my ideal gas law again to convert to liters of O2. So then if I do that here, once again, so in this case, PV equals nRT, and I want to solve for volume. So volume is going to be equal to nRT over P. And again, I'm going to use the ideal gas law here, or this constant here. So that's going to be equal to the number of moles. So 0.334 moles multiplied by R, which is 8.31. And again, that's going to be kilopascal liter over Kelvin mole, and multiplied by the temperature, which is 298. So I'll just put this right here, 298 Kelvin. And then that's going to be over the pressure, which is which is going to be 100 kilopascal. So 100 kilopascal. And when I calculate this out, let's double check to make sure all the right units cancel out. So moles here, moles there cancel out. Kelvin there cancel out. And kilopascal cancel out. I have liters left, so that's a volume unit. Awesome. And so now I can do my calculation. And when I calculate it out, I get 8.28 liters of O2. So this is the volume of oxygen required to completely react with the amount of CH4 that I have. Okay, so that's part A. What about part B? Okay, so part B of this example problem is asking us how many grams of H2O are produced. So in this case, I want to know the grams of a product, in this case, water vapor. Now in part A, I have calculated the number of moles of both the CH4, which is methane, and the moles of oxygen. So in this case, I can use either one of those to use stoichiometry, normal stoichiometry, to go from moles of one of those to grams of water. So let's get into this. So here, I'll use the moles that I calculated before. So the moles of CH4 that I have. So the moles of CH4 was 0.167 moles of CH4. And then I can use the mole ratio of my balanced equation. So here it's a 1:2 ratio. So here, so I'm going to put 1 mole of CH4 on the bottom, and I have 2 moles of H2O on top. So the moles cancel out. And now I can use the molar mass of water to convert moles to grams. And so the molar mass of water is 18.02. So 18.02 grams for every mole of water. So 1 mole of water on the bottom and 18.02 grams on top. So moles cancel out. And then when I do the calculation, I get 6.02 grams of water is produced. Now, I could also have done this with oxygen. So if I use the moles of oxygen that I calculated in A, that would be 0.334. So I have 0.334 moles of O2 over 1. And again, I'm going to use the mole ratio in my balanced equation. So this time I'm starting with oxygen. And so here I have 2 moles of oxygen and 2 moles of water. So it's a 1-to-1, but I'm just going to use the coefficients because I'll let the math simplify itself. So here I have 2 moles of O2 on the bottom and 2 moles of that should be H2O. I was about to write CH4. Okay, H2O. And then the next step is now I can use, again, the molar mass of H2O to convert. So here, 1 mole of H2O on the bottom and 18.02 grams of water on top. So here, moles of O2 cancel out, moles of water cancel out. And here, again, I get 6.02 grams of water. So either one of these you can use to convert to the grams of water. And so this is just a basic stoichiometry problem. No need to use any gas laws here. Okay, what about part C? Yes, there is a part C, so let's do that one. Okay, so part C is asking us what volume of CO2 gas at STP is produced if only 2.15 grams of the CH4 was burned. So we're given 2.15 grams of CH4, and we want to know what volume of CO2 would be produced at STP. So there's a couple of ways you could go about this. The first way would be to convert your grams of your CH4 to moles, and then using the molar mass of CH4, and then convert moles. So let's write this out. So we want to go from, So the first step would be to go from moles of A, which is our CH4, to, not moles of CH4. That would be grams. So grams or mass, the mass in grams of CH4 to moles of A, which is our CH4, using the molar mass. So we're going to use molar mass of A. And then using our mole ratio to go from moles of A to moles of B. So we're going to use the mole ratio between A and B, and then use our PV equals nRT to go from moles of B to volume of B. So we're going to use PV equals nRT here, right? So that would be one way to do it. The other way would be, or we could use the molar volume at STP, which is 22.4 liters. So 1 mole of gas at STP is 22.4 liters. So we could use that conversion factor. So either way should work. So let's go ahead and do both. So the first thing I want to do is take 2.15. So I'm going to take 2.15 grams of the CH4. And I'm going to use the molar mass of CH4 to convert to moles. And so that's 16.05. So 16.05 grams of CH4 on the bottom, 1 mole of CH4 on top. So grams of CH4 cancel out. Now I can use the mole ratio between the methane and CO2, which is 1 to 1. So 1 mole of CH4 on the bottom, 1 mole of CO2 on top. So moles of CH4 cancel out. And so then I can calculate the number of moles of CO2, and that's going to be 0.135 moles of CO2. So now that I have the moles of CO2, I can now use my PV equals nRT. And so I'm going to go ahead and write that up here. So PV equals nRT. And I have moles, and I can convert everything to the proper unit. So I want to find volume since we want to know volume. So I'm going to solve for volume. Volume is equal to nRT over the pressure. And now I just plug everything in. Of course, it says STP. So STP, that's going to be standard temperature and pressure. So temperature is going to be 273 Kelvin or 0 degrees Celsius, but we need it in Kelvin. So it's going to be 273 Kelvin, and pressure is 1 atmosphere. So then I just plug that in here. Or again, kilopascals, that's going to be 101.325 kilopascals. So since I have kilopascals here, I should have my standard pressure in kilopascals. Okay, so my moles, I have 0.135 moles. R is going to be 8.31, and that's going to be kilopascal liter over mole Kelvin. And then the temperature is going to be 273 Kelvin all over the standard pressure, which is 101.325 kilopascals. Okay, so far so good. And then so kilopascals cancels out here, Kelvin cancels out there, moles cancels out here. Now I'm left with liters. So when I do the calculation, I get 3.00 liters of CO2. Okay, so that's one way to do it. The other way to do it is instead of doing this, I could just use the molar volume to convert. So then here, since I know 1 mole is equal to 22.4 liters of a gas at STP, I can just go ahead and use that as conversion factor. So here 1 mole of CO2 is going to be equal to 22.4 liters of CO2. So moles cancels out. And if I do that calculation, I once again get 3.00 liters of CO2. So either way works. Okay, so that's example number 1. And then stay tuned for examples 2 and 3 at another video where I will continue. If you enjoyed this video, please by all means like this video, hit that like button right there. Also share the video with your friends. Subscribe to my channel, by the way. Hit the notification bell. And also when you hit that bell, make sure you click all so you should get notified by all the videos I put out. And also finally put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.